In this video, we're going to pick up where we left off in part 1, having determined the spectral type, effective temperature, luminosity, and mass of our star. If you're coming to this video having not seen part 1, then you need to go back and watch that video first, as we will need all of the parameters we defined in that video for this one. Link in the description and card above. The first important parameter that we're going to calculate is our star's radius. To do this, we're going to use this equation, which states that the square of our star's radius is equal to our star's luminosity, in watts, divided by 4 pi times the Stefan-Boltzmann constant times our star's effective temperature, in Kelvin, raised to the 4th power. The Stefan-Boltzmann constant, which we represent with the Greek letter sigma, just relates the star's energy output to its temperature and is equal to a value of 5.6703744419 times 10 to the power of negative 8 watts per square meter per Kelvin to the 4th. Yes, that was a mouthful. But don't worry, it's not necessary that you understand any of that. Let's jump over to our calculator and start by entering our star's luminosity. As usual, because we're dealing with a number in scientific notation, we want to put it in parentheses. My star's luminosity, as I defined in the previous video, is equal to 2.5858 times 10 to the 26 watts. Then we divide. Now, for this calculation to work out correctly, we need all the terms after the divide encapsulated in parentheses as well. We then enter 4 pi. Some calculators require you to type 4 times pi, but this calculator assumes that they're multiplied together. We then enter the Stefan-Boltzmann constant. Once again, it's in scientific notation, so we put it in its own parentheses and type 5.670374419 times 10 raised to the power of negative 8 and close the parentheses. Now we enter the effective temperature of our star. Mine was previously defined as 5,492 Kelvin. We then raise our temperature value to the 4th power and close our second parentheses. So your calculation should look something like this. When we press equals, we get this large number, which is not the number we want. Remember, this is the square of our star's radius. So to calculate the radius, we need to get the square root of this number. Now in this case, there are 2 ways we can go about doing this. The first is to clear this and then press this button here, followed by the answer button, which will give you the square root of the number we just calculated. Now that's unarguably very simple and convenient, but only in this circumstance. What if we needed the cube root of a number, or the 4th root, or the calculator we're using doesn't have that button? Another way that we can get the square root, or any root, is by raising our number to a power of 1 over the root that we need. So for instance, if we wanted the square root of a number, we could raise that number to the power of 1 over 2. If we wanted the cube root, we could raise it to the power of 1 over 3. The 4th root, 1 over 4, and so on. This is the method that I prefer to use due to its versatility. Now you can either enter it as a fraction, 1 over 2, or as a decimal value, 0.5. But if you enter it as a fraction, be sure to put it within parentheses. Otherwise, the calculator won't read it correctly. Anyway, we get the square root of our number through whichever means you want to use, and this gives us the volumetric radius of our star, represented in meters. So now we can write it down on our sap sheet. While we still have our radius on the calculator, we can divide it by the radius of the sun to convert our radius into solar radii. I've said radius too many times. So that's divided by 695,700,000 meters. Press equals, and there's the size of our star in comparison to the sun. If you got through all that, congratulations. That was the most complicated of the equations we're going to be using in this video. So it should all be smooth sailing from here. The next important parameter that we're going to calculate is our star's surface area. To do this, we just need this simple equation, which equates the surface area to 4 pi times the radius of our star squared. So for my star, that's 4 pi times 631,575,985 raised to the power of 2. We press equals, and there's our star's surface area. I'm going to record it on my sap sheet as 5.0126 times 10 to the 18 square meters. The next important parameter we're going to calculate is our star's volume. To do this, we're going to use the surface area that we just calculated, multiply it by our star's radius, and then divide by 3. So I'm going to click multiply, then enter my star's radius, and divide by 3. This will give me my star's spherical volume, and I can record it on my SAP sheet as 1.0553 times 10 to the 27 cubic meters. The next important parameter that we're going to calculate is the star's mean density, which is given by this simple equation where the mean density is equal to the mass of our star divided by its volume. So let's start off by entering in our star's mass within parentheses. Then we divide it by our star's volume, also in parentheses. We then press equals, and there's our star's mean density in kilograms per cubic meter. Now, with this parameter, it's not necessary to get anything past the decimal point, but I'm going to round the last digit up and record it to my SAP sheet as 1,708 kilograms per cubic meter. If you've made it this far, congratulations! You have defined all of the important parameters for your star that we're going to cover in this video. The 3 remaining parameters are all optional and just provide extra details about your star's behavior. The first of the optional parameters is the star's mass conversion rate. This is how much of its mass is being converted into energy per second, and uses this equation, where the mass is equal to the luminosity of the star divided by the speed of light squared. Before we do this calculation, let's save ourselves a bit of time going forward. All of these optional parameters start with the luminosity, and I don't want to have to enter in the number over and over again. Unfortunately, this particular calculator doesn't have any memory buttons, so what I'm going to do instead is enter my star's luminosity and press equals. Then, when I want to retrieve this value, I can go over here to the history icon and find my luminosity value. Then all I have to do is click it to put it into the calculation. Now that we have our luminosity, we want to divide it by the speed of light squared, which we do by entering 299,792,458 meters per second, and then square this by raising it to the power of 2. Now, when I press equals, I get a number that isn't being displayed like all the previous results I've had. That's because this calculator only displays numbers in scientific notation when they're over a certain size. This number is below that threshold, and so it's displayed as a normal number. But I want it in scientific notation. So all I have to do is count the digits between the highest number and the decimal point. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So my star's mass conversion rate is 2.8771 times 10 to the power of 9 kilograms per second. That's nearly 3 billion kilograms of my star's mass being converted into light every second. That's kind of mind-blowing. Anyway, moving on. The next optional parameter is the star's mean energy production. This is a measure of how much energy your star is producing from each kilogram of matter. It is given by this equation, where the energy is equal to the star's luminosity divided by its mass. So once again, I'm going to click the history icon and select my luminosity value to start the calculation. Then I'm going to divide it by the mass of my star, which is 1.8024 times 10 to the 30 kilograms. Pressing equals, I once again get a value that is not in scientific notation like I want it to be. But instead of being a very large number, this is a very small one. So this number will be multiplied by 10 raised to a negative value. To find that value, I can simply count the number of zeros in front of my number, which in this case is 4. So my star's mean energy production is equal to 1.4346 times 10 to the negative 4 watts per kilogram. Our last optional parameter is the star's surface emission, which is a measure of how much energy is being released by every square meter of the star's surface. It is given by this equation, where the star's luminosity is divided by its surface area. I'm going to retrieve my luminosity value one last time and then divide it by the surface area that I calculated earlier of 5.0126 times 10 to the 18 square meters. Pressing equals gives me a value of 5.1586 times 10 to the 7 watts per square meter. So every square meter of my star is emitting over 51 million watts. If you've made it this far, congratulations. You now have a very detailed and realistic star for your planetary system. There's only a handful of important and optional parameters left to define, but as they do require a bit of explanation, I will cover those in subsequent videos. I hope you will join me for that.